A pleasure to be here, and thank you all for joining. I hope that I understand most of you are with a hydrological background. So I hope that what I have to say is relevant for your work. But please feel free to contact me offline or after the seminar if you'd like to engage in further discussion. So I'd like to give kind of a broad brush talk about the combined effects of internal variability and anthropogenic influences on regional climate trends. And I will not just focus on Europe, but I'll demonstrate this concept and how it plays out for both North America and Europe, drawing largely on some recent papers from my group, and based on, a work of many people over the years. Okay, so again, I like to cast this concept as thinking about a range of outcomes. So anthropogenic climate change is accelerating, and we can all feel the impacts now pretty much no matter where we live. But that anthropogenic component of climate is going to be superimposed upon internal climate variability. And this internal climate variability has limited predictability and also has long timescales. So variability can exist on over multiple decades. And this makes it tricky to easily disentangle these two influences. So I'm really going to address how do we disentangle anthropogenic and internal variability at local and regional scales where we live and work and where it's most impactful. And then I will also then talk about a related question: how do we make sense of climate model projections given this ubiquitous internal variability? And we're all familiar, of course, with the IPCC and the CMIP set of model simulations that are widely used. And I think sometimes they are misused or misinterpreted. And I'd like to just sort of highlight some of the ways that I think are more sensible uses of these projections. And these two questions really are called out as outstanding challenges in all of the IPC assessment reports, including the latest one. So these are still issues that we have in our field. If you'd like more reading, I'll just advertise that there's a lot more detail in a recent paper published by myself and a colleague, Adam Phillips, where it's dedicated results for the European sector. So if you'd like more detail, please feel free to read this paper. Okay, so outline of the talk, and again, I'm just keeping it at a high level. So I'm just sort of introducing things one by one. And first, I'll just get us on the same page about what I mean by internal climate variability. Then I'll get to the meat of the talk, which is how we use climate model projections and how we make effective use of these projections. Then I want to step back and look at our observed climate system and talk about how to interpret the trends that we have seen. And then finally, just a few remarks on model evaluation strategies given these issues. And then finally, just a very brief summary and outlook. So internal climate variability is ubiquitous. It occurs everywhere, and it stems from chaotic fluctuations within the atmosphere, within the coupled ocean-atmosphere system, and within the ocean itself. And of course, the land and the cryosphere can also produce important effects as well. But these are the primary realms where internal climate variability exists. So for example, if we just take the case of the atmosphere, weather, day-to-day, week-to-week variability in our weather systems at middle latitudes is really largely governed by the jet stream. And this is just an example for February 2015 over the US, where we had a very polarized country, not only in terms of climate or weather, but also, of course, politically. And we've seen many examples over the years and months where these are continental scale impacts from the jet stream. And the important part here is that predictability is limited, maybe a few weeks at best, due to simply the nonlinear dynamics within the atmosphere that produces this variability. And it can be considered sort of as sort of a noise, white or red noise, which means that the variability also has a long tail that can encompass very long time scales, including decadal to centennial. And I think a lot of people miss this fact that the atmosphere alone, although it's not predictable beyond a few weeks, can nevertheless contribute variability on these long time scales. And one can think of this as a random stochastic process that occurs, and there are seminal papers listed here. Okay, then we can move to the coupled system between the ocean and the atmosphere. And when there is this interaction, then this gives rise to a set of what we call modes of variability. A lot of people use oscillation. That's not meant to be oscillation in time, but it's actually a seesaw in space. But nevertheless, these are modes of variability that occur from monthly up to multi-decadal timescales. And I've listed some of the prominent modes here. And again, for the purpose of this talk, the salient or the important feature here is that predictability, although it does exist, and it's extremely important that we have predictability of these modes, nevertheless, it's still limited. So for ENSO at this point, roughly up to 2 years, in some cases, less in other cases, maybe 5 years for the Pacific decadal oscillation, and maybe some skillful predictions up to 10 years for the Atlantic multi-decadal oscillation, although I would say these are on the sort of upper bounds at this point for predictability. And then finally, the ocean, I won't speak too much about it, but it has, of course, it's also fluid. It has its own chaotic motions, and these can give rise to variability within the ocean. Okay, so this is my last slide about internal climate variability, and I like to use this analogy with the roll of the dice. So we have these modes of variability, we have weather, we have ENSO, etc. And once you get beyond the predictability time horizon, which is weeks to a decade, as I've just shown you, then you can consider these modes of variability as simply a roll of the dice. And so we don't know how they will play out once that memory or that predictability is gone. And then we have to consider these as just random fluctuations that are superimposed on the human-induced climate change signal. So in a nutshell, this introduces unavoidable uncertainty to climate model projections, and it complicates climate model evaluation and presents challenges for attribution of observed climate trends, especially at these local and regional scales. I'm not at all arguing about the global scale averages, but I think especially when we get to these local scales or regional scales, this is a really big issue, and it's not going to go away. Internal variability is just part of the way our atmosphere and oceans work. And we have to recognize that it exists and be sensible then about what we can say about climate model projections. Okay, so now I'd like to move to the heart of the talk, which is making sense of climate model projections. And I'm going to emphasize insights that we have gained as a community over the last 10, 20 years from so-called initial condition large ensembles. And I will tell you exactly what these are and why they are very useful in a moment. I just want to give you this reference from a US CLIVAR working group on large ensembles that I led with Keith Rogers a few years ago. And this is a kind of a summary paper from the entire working group published in Nature Climate Change about what these are, what kind of insights you can gain from such large ensembles. And if you're interested in further reading, it's meant for a general audience. So I hope that can be useful if you're interested. Okay, so I'm going to talk about what these large ensembles are, and specifically I'm going to call them initial condition large ensembles with models. And I'm going to use as my example one of the most successful projects because it was a community-oriented project. And many, many people now have used the output from these simulations in their research. And I think it's been very valuable for the entire community. And these are all publicly available simulations. So this was, as I say, really a community resource for studying climate change in the presence of internal climate variability. We have lots of, on the website, we have, made it hopefully easy for people to navigate how to get the data and what the data can be used for. Lots of citations to date on these simulations showing their utility for the broad climate research community. There was a huge effort at the time, and took 600 terabytes of data, maybe not so much these days, but back in 2014 when we did these runs, this was a big deal for NCAR to actually decide that this was an important endeavor. Okay, so CSM1 is the Community Earth System Model version 1. We now have a version 2 and are developing version 3. So it's a global coupled model. It has a spatial resolution of about 1 degree in latitude and longitude. So as these models, global models go, it's considered a fairly high resolution model, although now other modeling centers, including NCAR, have some higher resolution models as well. So I call it, use this crystal ball, which, all of us are using to be able to say something about what might come down in the future for our climate system. Okay, so the way that these simulations are configured, I'm going to now illustrate here, and it's important to understand them so you can appreciate then this interplay between the internal variability and human-induced climate change. So very typical of all of these CMIP kind of models, which I'm sure you're all familiar with. First, in this green line, one runs kind of a control run of the model under fixed radiative conditions from the pre-industrial, quote, time period. Often 1850 is taken as that time. So this includes, all the known radiative forcings, solar volcanoes, etc. And they are fixed at these conditions. And then the model is run so that it reaches some kind of equilibrated state between the ocean and the atmosphere and the cryosphere, etc. And then one begins a so-called historical run and then a future run with prescribing a time evolution of radiative forcing. So in our case, at year 401 from this 1850 control run, we deemed the system, the model system, to be sort of quasi-equilibrium, and we began our historical runs. So the historical run, maybe I'll just go back a second here. One prescribes from 1850 to present day the observed historical evolution of radiative forcings, meaning greenhouse gases, anthropogenic aerosols, solar variability, volcanism, etc., as we're all familiar with. And then for the future part of these simulations, one chooses a future scenario. In our case, we chose this representative concentration pathway 8.5. So 8.5 watts per meter squared by the end of the century. So what's new here compared to the typical simulations is that we did a large ensemble. So we chose 1920 as our departure point or initialization point. And at that time, on January 1st, 1920, we introduced a tiny perturbation to the atmospheric temperatures in the model. And this was on the order of the round-off error of the model, i.e. 10 to the minus 14 degree Kelvin. So truly, this so-called butterfly effect, you could never have measured that. So we introduce this perturbation, and we run another simulation. And we do this another 39 times. So we have a total of 40 simulations. So they all run with the same historical and RCP 8.5 radiative forcing. It's the same model. So if these simulations diverge from one another as they, as you move forward in time, that divergence or spread can only be due to internal variability because it's the same model and the same radiative forcing for each of these simulations. And then we also know that spread, once you're beyond this predictability time horizon, is therefore irreducible and it's largely unpredictable. So I'm going to use the hammer here to convey the forcing or the forced response, and the butterfly to convey this notion of internal variability as we go through the talk. And then the nice thing about having so many simulations is that you can isolate the forced response, or at least get a very good estimate of the anthropogenic or radiatively forced response at each time step and location by averaging across the members. And the reason this works is that the internal variability as it plays out, once it's no longer predictable, will have a different phase, a random phase and amplitude amongst each simulation. So if you have enough simulations, then when you average them, that internal variability will average out, or at least become very small. So you can get a good estimate then of the forced response. The number of simulations that you need for a good estimate of the forced response is dependent on the spatial scale of interest, the particular variable of interest. It may be larger for precipitation than for temperature, for example, and larger, say, for variability compared to mean state changes. These are all issues you can read about in that working group paper. Okay, now just to say that we have now released a newer large ensemble with the new CESM model version 2, and this has 100 members, so bigger and better perhaps, and all of them run from 1850 to 2100. So we've started them way back, and they use this so-called SSP 370 forcing scenario. So again, if you're interested, all of these model output are available. Okay, I'm going to get on now with the talk. So just again to hammer home this point about the butterfly effect. So this is, you're looking at global mean temperature from the CSM1 large ensemble for the first 60 days. And we introduce this perturbation 10 to the minus 14 degree K. I guess here maybe it's day 6 or something. And then you can see after about a week or two, you can see this butterfly effect, taking place. And even on this global mean temperature, you can start to see the different simulations diverge. So that's the weather time scale. Now we look across the entire simulation time period, 150 years. And this again is global mean surface temperature. Now we've removed the mean over, I've forgotten exactly which time period, doesn't really matter, some reference historical period, so sort of centered around 0 here. And you can see the control run in blue, and then the first member that was begun in 1850, that's in black. And then that goes all the way to 2100. And then the gray are all the individual members from 1920, their starting point to 2100. So it makes this little cloud. And then the observations are in red. So for the model, at least one benchmark for model credibility is that the observed global mean times temperature time series needs to fall within the spread of the ensemble, which it does. And this was a very important aspect of the realism of CESM1. Okay, so you may say, well, why bother with so many simulations if they don't look that different on the global scale? Well, that's a very valid point, but now we will look at these local and regional scales. We'll look at maps, and I'm going to show you trends where I fit a linear trend to the data over the next 50 years at each grid point. And I'll show you that when you look at it on these finer scales, that it does matter, or it is important to have so many simulations. So first I'll illustrate for North America, and then we'll look at Europe. Okay, so again, future changes, a range of outcomes. That is my theme. And this is a figure that is taken from a very brief paper that I did in 2020 in Earth's Future. It's going to show you a map of the linear change in temperature, in winter precipitation over North America, roughly over the next 50 years. So our crystal ball. Okay, so this map is showing the average of the entire ensemble, so all 40 members. So again, my hammer is to convey that this is an estimate of the anthropogenic influence, because we've averaged out most of the internal variability. So according to this model, like many other models, winter time precipitation is expected to increase under the influence of rising greenhouse gases, and especially on the West and East Coast. So nothing surprising here. Now so this is what we expect. This is kind of a phrase I borrowed from Mark Twain, and maybe it goes back to someone else earlier. So, okay, that's all well and good, but now let's look at some individual members. So here is one member. I selected it because it's in the tails of the distribution. So for the continent as a whole, I picked the ensemble member, or the simulation, that had the second wettest trend on average over the continent. So you can think of this as being in the wettest 5th percentile of these 40 members, top 5th percentile. So the pattern looks a lot like the anthropogenic influence, but the magnitude is much larger, especially on the west and east coast. So this is one member, and this is what is possible according to the model. Here's another member, and this I chose from the dry end of the tail of the distribution. So it's the second driest member, roughly corresponding to the bottom fifth percentile. And here it gives a very different outlook for precipitation over North America. In fact, much of the southern 2/3 and western 2/3 of the continent actually are projected to dry. So obviously, internal variability has been able to overwhelm the anthropogenic influence in terms of sign of change for this member. And for the other member, the wettest one, it's been able to augment the amplitude of the anthropogenic influence. So each of these individual members are what we might get according to the model. So we may not necessarily just see the anthropogenic influence when we're looking at trends over the next 50 years. We're going to get some combination of internal variability and anthropogenic influence. And these two maps on the bottom are meant to depict kind of the range of outcomes, the plausible range. Think of it as the 95th percentile range of outcomes according to this model and this radiative forcing scenario. So it's really important for, it's just very, very important. So as I say, that's the plausible model range, i.e. the 95th percentile range of outcomes due to internal variability. Okay, I always speak slowly and I can never get through all my slides, but my main purpose here today is just to illustrate concepts with some concrete examples, and the details are in the papers. Okay, so now I'd like to show you the same thing for the European sector. So this is from a newer paper published just earlier this year in Nonlinear Processes in Geophysics. If you're interested, that's the paper that I cited earlier. So here I'm showing you a very similar depiction. So we're looking at, again, wintertime precipitation trends over the next, linear trends over the next 50 years. So the middle map, the ensemble mean, that can be interpreted as the anthropogenically forced component. I forgot to say that these results are from the new CESM2 100-member large ensemble. So we have a really, such a large ensemble that we are really getting a very accurate depiction of this forced response in the middle map because we have so many ensemble members that we've averaged. So as expected, as we're physically understanding that the northern part of the continent is expected to get wetter and then drying over the regions surrounding the Mediterranean. Now on the left and the right, these are the individual members. The wet member is taken from the from within the top 5th percentile of the 100 members. So that's the wet end of the distribution, and the member on the right is taken from the driest 5th percentile. So these are individual members in the top and bottom 5th percentile tails of the distribution. And you can see very different outcomes at each location. It's really amazing. You can look at Scandinavia, for example, and they have almost opposite sign, as do areas in Spain. The UK, I guess, is always going to get wetter, but the magnitude can vary very appreciably. Then I just want to point out that this is not happening. How do we understand these changes Well, it's very important to look at them in terms of the context of the large-scale atmospheric circulation. So here I'm showing you in the contours the linear change in the barometric pressure at sea level. So sea level pressure in the contours here from these simulations. And I've just indicated the low and the high pressure. These are linear trends. And you can see on the left that that member that has a lot of increase in precipitation, the wet member, it features a low pressure trend centered over the UK. And that's really driving a lot of this increase, enhancement of the precipitation increase in that member. Whereas if you look on the right-hand side, the dry member, it has a high pressure trend centered over southeastern Europe and the Middle East. And that is driving, a lot of this drying that we are seeing here. So the variability or the impact or the contribution from the internal variability on precipitation is largely driven by this internal variability of the atmospheric circulation. And then I'll just bring in temperature also, just for if you're interested. So again, the same kind of selection. The middle is the forced response, and then the end members are shown on the left and the right. And again, you can see that although the continent as a whole will warm in most areas, no matter which member you select, the amplitude of the warming can be dramatically different. And again, that's dependent on the configuration of the atmospheric circulation. Okay, so I'm running very slowly here in my speech, so I may end up skipping a bunch of slides. So you feel free to close your eyes, but I'm just going to try to select the ones that I think are the most important. So I'll just move on quickly here to another way to show this information. And this is in terms of the risk of anthropogenic climate change. So again, I'm casting this as this roll of the dice from the unpredictable component of internal variability plus the anthropogenic climate change, the hammer. And this is an older paper, but trust me, you can read the newer papers. The results are very analogous for Europe and also based on the newer CSM2 model. So this is another way to portray this information. So this is the chance of having an increase. I'm not saying how much, but an increase in wintertime precipitation over North America in the next 50 years. And what we do is we have 40 simulations. We simply count up the number of members that have a positive trend at a given location, and then divide that number by 40, the total number of simulations. And that's the percentage of members that are showing a positive trend in wintertime precipitation. So I'll walk you through the diagram. So Canada here, very highly likely, greater than 85% chance, and even greater than 95% in the farthest north, that the winters will become wetter. So, it's virtually guaranteed. California and other parts of the West, the blue here would signify, the chance of a drier winter, these lower numbers. You can kind of invert the color bar. And, still better than 50-50 odds of drier winters, but it's not guaranteed. And then the whole middle 2/3 of the country, roughly equal chances of wet and dry. I don't think we get the same information when we look at just the anthropogenic or the ensemble mean, influence, anthropogenic influence, what the chances are of having, a future next 50 years wetter or drier winters. We really need to take account of this internal variability to make these calculations. So I think this is a very important and effective way of communicating this interplay between the internal variability and the force response. So as I said, you can find European results in an older paper in 2017 and then the newer 2023 paper. Okay, so briefly interpreting the observed record. So I've been showing you all these future projections. Now we can step back and we can say, reality gave us certain trends that we have, observed. How much did internal variability contribute to them, and how much did human-induced climate change contribute? So this is obviously a really, really important question that can be addressed from many viewpoints. I'm just going to illustrate things here based on these model large ensembles. So I'm going to illustrate it. I think in this presentation, I'm going to focus mainly on North America, but we've done very similar calculations for Europe for precipitation. I think I'll show you that in a moment. So wintertime air temperature trends over roughly the last 50 years. This is an older paper, so we ended our data set in 2012 here. So we had a lot of warming in the wintertime over the last 50 years, especially in Canada and Western Canada. So you might think, okay, that's very consistent with anthropogenic climate change. So what does our model tell us now that we've looked now at this issue of internal variability? So here is the CSM1 large ensemble. I picked out a particular simulation. This happened to be number 7 that we ran. And that's what it looks like. And it's a beautiful rendition of the observed trend. So, the model nailed, really did a great job, apparently, simulating the observed trend. So if we only had this one member, it would be difficult to interpret either one, the observed or the simulated trend, with just one member. So let me show you another member. This is number 25, same model, same forcing. It gave us cooling over parts of the West and then muted warming over parts of the East. So extremely different from the other simulation. And these two simulations differ only because of the internal variability. So this raises a lot of questions. And these are the questions that, we try to answer in our papers, and many, many people are answering from many different approaches. So why are they so different? I don't have time to walk you through this particular example because I want to get to a few other things, but they differ because of the atmospheric circulation. So I will skip that part because I think I've already made that point. Secondly, here's what I want to get to. Could another reality have been possible? So we know in the model world, many different realities are possible. You're looking at 2 of them here, the 7th and the 25th simulation. These are very different outcomes. So then we step back to the real world and we can ask, maybe the real world could have looked different also if the internal variability had been sequenced in a different way. So that's what I'm going to show you next. And then the third thing that I'll end with, as I said in my outline, given these issues, how should we evaluate and compare climate models? It's tricky. You really have to take rigorous account of the internal variability. So I'm going to talk about could another reality have been possible. And let me just skip, I'm going to skip a bunch of slides to get to that part. So you're welcome to look at these pretty pictures in my paper, but I'm skipping this, and excuse me for doing this. I hate when people skip over things, but I just want to get to this important issue. Could another reality have been possible? And the answer is absolutely yes. And the way that we have quantified this is we've tried to construct a synthetic large ensemble based on observations. So we take the observed data. This was a postdoc of mine, Karen McKinnon, who led this work, and it's still ongoing. So we take the observations, we take all of these modes of variability that we have observed and observations of weather, and we take the data from 1920 to 2016, in our case, when we did the first study, and we randomly shuffle the data in time. And we do this on detrended data. So we're trying to isolate the internal variability, although, of course, imperfectly, but that's what we're doing. We're trying. And then we randomly shuffle the data in time, but while preserving the statistical properties of the observed variability. And what I mean by statistical properties, in particular, the variance, the temporal autocorrelation, and the spatial patterns. And you can read about the methodology if you're interested in these papers, just to say that we tested how good our methods are using this perfect model framework, if you will, of the CSM1 large ensemble, where we know, what the truth is. And we find that actually over most areas, it's less than 10%, maybe a few areas where the error can reach 20%. So it's pretty good. Okay. And then we shuffle the, our estimated internal variability from the observations. And then we add the forced response from models or something else that I call the observed thermodynamic residual, which I had to skip over here for lack of time. And then I can show you what alternate realities could have occurred if we had had a different permutation or sequence of internal variability. Okay, so we'll come back to our example for North America. This was the actual observed trend over the last 50 years, roughly, of wintertime air temperature. And now I'm going to show you this result of this synthetic, observationally based large ensemble. We have 1,000 members. You can run as many members as you want. It's a very quick statistical model. And now I'm showing you this 95th percentile range of trends. So this member here on the left, lower left, that's the member that was lying at the 2.55th percentile for North America as a whole in terms of the temperature increase. And then the other member on the right is at that 97.5th percentile. So that's these two maps depict the range, the 95th percentile range. So these are the alternate realities that the real world could have given us, where we use the forced response from the model and the range of internal variability from observations. So very, very large. And just to show you here, I've circled from the CSM1 large ensemble, these two members, which look a lot like the 95th percentile range from our observational large ensemble. So the model is not out to lunch. Like the model has a really good depiction of this internal variability range. So the same results are happening for Europe, and I'll just show you here observed precipitation trends over the last 50 years over the Eurasian domain, European domain on the left are the observed, and then the middle panel, I haven't explained it, but that's our observational estimate of the forced response. I apologize, you can ask me in the questions what that is exactly. And then the wet and the dry members, those are, again, finding a member within that, lying at the 2.5th percentile of this observational large ensemble, and the dry, sorry, that's the 97.5th and the dry at the 2.5th. And so you can see that, again, alternate realities were possible. And that is, for me, that was a real take-home message. You don't have to just think about the model world, but wow, reality could have been really, really different. And then just to show you a comparison, so on the bottom here, this is all from the model. The top row is all from observations. The bottom is all from the CSM2 model. And if you look at the ensemble, well, if you look at the wet and dry members, they are what we estimate from the observations and what we get from the model are actually, in terms of precipitation trends, they're really similar in their spatial pattern. So I think the model is very credible and is telling us some important information. And we can assess the model when we have this observational large ensemble. Okay, so closing remarks. I'm not going to show you any more figures, but closing remarks. So model evaluation strategies. I'm not going to show you how to do it, I'm just going to raise, I think, the important questions that we have to address when we are evaluating our climate models. So the first is, do the observations lie within the spread of simulations from a model large ensemble? So what you need for a credible model is that the range of outcomes due to internal variability and anthropogenic forcing, that the observed trends need to lie within that distribution from the model. You don't want a single simulation necessarily to match the observations unless you have, a huge number of simulations. But the observations do have to lie within the spread. Secondly, if the model overestimates the amplitude of internal variability, then it's very easy for the observations to lie within the spread. So that's, not giving the right answer for the wrong reason. So you really have to then assess how well does a model simulate internal variability. And that in turn has a lot of challenges because the observational record is quite short. And there's a lot of papers, I've been involved in many of them, to assess how well do we know the patterns and amplitudes of internal variability from the limited observational record. And then thirdly, when you want for comparing models with each other, if you want to assess whether the models really are structurally different, you need a lot of ensemble members, because maybe model A has a wet future and model B has a dry future. But those differences could have just been due to how the internal variability happened to play out in those individual simulations. So you need a lot of simulations with each model to really assess whether models have structural differences. Okay, and then some tools from my own group here at NCAR. I'll just point you to the Climate Data Guide that gives you a lot of information on observational data sets. And this is like the collected wisdom of the international community. And we're always looking for people to write up information on data sets. So I invite any of you to contact us if you have data sets that are not on the Climate Data Guide. And then the Climate Variability Diagnostics package for large ensembles. A lot of my figures were actually taken from this tool. It's an automated package. You don't need to know anything about the coding. It'll just give you these trend maps and evaluation of modes of variability. Okay, and then if you're interested in using these model large ensembles, we have collected here at NCAR in my group a bunch of the CMIP5 and CMIP6 models that have at least 15 ensemble members. And we're about to expand this set of models and expand the set of variables that we are outputting. So we just want to make it as easy as possible for the community to access these simulations. Okay, so summary and outlook. Again, point you to this paper if you're interested in details for the European domain. So just reminding you that anthropogenic climate change may be difficult to untangle from internal climate variability at these local and regional scales. And I hope I've shown you the utility of initial condition large ensembles with fully coupled Earth system models that provide new insights and understanding. And if you're interested in large ensembles, further reading, there's the working group paper, and then pointing you to these tools. So thanks so much for your attention, and I'm looking forward to your questions and discussion.